Hi everyone, good evening. In this lecture series, we are going to see the unit mobile radio propagation. The first topic we are going to discuss in this lecture series is free space propagation model. So what do you mean by propagation? It is nothing but a term. It is used to describe the signal transmitted from the sending station to the receiving station. We are going to analyze and ensure the performance of the wireless communication systems. And what are all the propagation models we are using? It will be of low cost, and the propagation model is used to predict the average signal strength, received signal strength. So this is the free space propagation model diagram. So what I have mentioned is it is used to predict the received signal strength. The transmitter and the receiver have an clear unobstructed line of sight between them, and it will predict the received power. Which decays as a function of the transmitter receiver separation distance. So for example, if we take an example for this propagation model, the satellite communication systems, just we are having the transmitting antenna and the receiving antenna, how the signal has been transmitted with the mic. Suppose if we are using the microwave, how the line of sight that will be transmitted through the transmitter and the receiver. So here we are mentioning one of the space equation, which is nothing but the free space equation. The free space power received by a receiver antenna, it is separated from the radiating transmitter antenna, and the distance will be d. So here the free space equation shows that the received power falls, and as well as that implies the received power decays at a rate of 20 dB. So what is the equation here? We are using the free space means PR of D. So we know that PT, it is nothing but the transmitted power. PR of D, it is nothing but received power with respect to that of the distance. PT GT G or lambda squared divided by 4 pi the whole square D squared into L. So GT and GR is the gain of the received and transmitted antenna. Lambda is the wavelength, D is the distance. So here L we are mentioning it as the system loss factor. So this is an activity. And the next one we are going to see the free space equation. Effective aperture, that is AE, is related to the gain of the antenna. G is equal to 4 pi AE divided by lambda square. So lambda, when it relates to the carrier frequency, that is lambda is equal to C by F. We know that if we substitute the value, we will get 2 pi C divided by omega C. Omega is equal to 2 pi F. So F is equal to we are having omega frequency is equal to 2 pi. So just we are substituting the equation, and we are getting the value of 2 pi C. The next one we are going to discuss about the free space equation. In free equation, we are having two types of the dimensional quantities, that is GT and DR, where T is the that is GT is the transmitted gain and GR is the received gain. Here we are going to measure the isotropic radiation pattern of an ideal antenna, which radiates the power with unit gain uniformly in all directions. So ERP is equal to EIRP. So this is the calculations in order to find the effective isotropic pattern. So it is nothing but PTPG. So how we are going to measure the path loss means the path loss is measured in dB, and we are going to take the difference between the transmitted power and the received power. May or may not be included the effect of the antenna gains. So here we are having the signal strength, and it will reduce the distances so that the path loss can be measured between the transmitter and the receiver. So here it represents the signal attenuation, and it is measured as A, and it is defined as the difference between the transmitted power and the received power. The path loss for the free space model, and when the antenna gain is PL of dB is equal to 10 log Pt by Pr. That is, we can write it as minus 10 log lambda squared divided by 4 pi squared into d squared. So this is the formula in order to calculate the path loss: minus 10 log GT lambda squared divided by 4 pi squared into d squared. So here we are mentioning the speed of light. C is the speed of light, and from that we have calculated. So here in case of the far field transmitting antenna, just we are having the isotropic, and we are going to measure the effective area from the transmitter to the receiving antenna. The next one, we are having the region. The Fraunhofer region is also termed to be as the far field, and the transmitting antenna is defined as the region beyond the largest linear dimensions and of the antenna aperture and the carrier wavelength. So the distance will be 2d squared divided by lambda. So next we are going to measure the close-in distance. So from that we have calculated the received power at the reference point. PR of D is equal to this value already we have mentioned in the path loss, and the received power levels, if suppose D is greater than or equal to D naught, that will be greater than or equal to the DL. Thank you.